Hello, and welcome back to Physics 41, University Physics 3. This is now the last chapter for this course, which will focus on alternating current. So, in the previous chapters, we already have introduced alternating current and basically gave you a comparison between alternating current and direct current. So alternating current is a current that changes value and direction, but DC current is a steady state current or a constant current, constant in value and constant in direction. So we also have discussed what happens when current flows through a resistive element, say such as a resistor or anything with a resistance. So there will be power loss. So power will be lost in a resistor, and it's proportional to I squared, the square of the current. So for the last chapter, we will be focusing on alternating current. So this chapter will involve circuits whose voltage is also alternating. So this is the symbol for alternating current and alternating voltage source. So before we proceed with the first lesson for this chapter, let us first review the lessons that the concepts that we need for the first lesson. So we actually need the concept of vectors. So in the first chapter, or in your mechanics, mechanics physics 21, University Physics 1, you learn about vectors. Vectors has a magnitude and direction. So the vector is represented by this arrow. The length of this arrow is the magnitude of the vector, and the direction of the vector is given by this angle theta. Now, if you want to take the component of a vector, say along the x-axis with an angle theta with respect to that axis, then you take the projection of that vector along this axis. And to get that projection, you just multiply the magnitude of the vector A times cosine of the angle. So we need this concept in discussing alternating current. So the first lesson for this chapter will be all about alternating current and phasors. So what is a phasor? So a phasor is actually a rotating vector. So a vector that rotates. So its direction, its magnitude may be constant, but its direction is always changing. So if you look at this pencil as a vector, say an arrow, then it's always rotating. It's always changing direction. So that's a phasor. So a phasor is not actually a physical quantity, but a geometric entity. And we use the concept of phasors in describing alternating current and alternating voltage. So, for instance, this is the phasor current. So its magnitude or its length is I. This is the maximum current. And you will notice that it will have a component along this axis. So this is actually the instantaneous current axis. So the value of the instantaneous current at a certain instant depends on the maximum current. Just like in taking the magnitude of a vector, it's A cosine theta. So in this case, the length of our phasor is I, and then cosine this angle. So this angle here, we are not given the angle theta, but we are given the angular frequency, the frequency of rotation of our phasor in radians per second multiplied by time, and that will give you an angle. So angular frequency is angle per second times time, which is second, then basically this is angle. The angle is omega times t. So you will notice that at different times, the value of our instantaneous current changes. So actually, if it is in this quadrant 1 and or in quadrant 1, the value of I is positive. But if the phasor is now in this direction, then the value of the instantaneous current is negative. So it's alternating, positive, negative, positive, negative. So actually, if it's in quadrant 3, it's negative. Quadrant 4, it's positive. So the values depends on omega t. Depends on the angle or in which quadrant is the phasor in. So we can actually define our instantaneous current as just I, the magnitude of the phasor, the rotating vector, which is also the maximum current. The maximum current, or what we call the current amplitude, cosine of the angle, which is given by the angular frequency, how fast is the phasor rotating, times the time. So take note that in a crude picture of alternating current, if we plot the instantaneous current I versus time, its plot will somewhat look like this. So it's alternating from a positive value I to a negative value of negative I. So I is the amplitude. It's the, when we discuss about waves, we discuss about amplitude. So it's basically that's the same concept. So the length, the maximum displacement. So in this case, the maximum displacement is I. So I is the location of the crest, and negative I is the location of the throw. So meaning the values of the current, the instantaneous current, varies from I, then less than I to 0, and then negative values to negative I, and it repeats. So it's sinusoidal. Okay. So we can also, since voltage and current are proportional to each other, then the voltage will also alternate. So the instantaneous voltage can also be written as the maximum voltage or the voltage amplitude cosine omega t. So in this case, in this region here, the voltage is positive, here the voltage is 0, and here the voltage again is negative. So the voltage is alternating from positive to negative values, and the actual value of the voltage also changes. So knowing the instantaneous current and the instantaneous voltage, we can now solve for the instantaneous power. So it's just instantaneous voltage times the instantaneous current. Now, since the values of our current and voltage are alternating, then how do you now describe the current and the voltage values? So one common way to describe alternating values is by taking the root mean square value. So this is used commonly to describe alternating and current and voltages. So for the root mean IRMS, or the root mean squared current, so it's just the square of all the values of the current, and then you take the average, and then you get the square root. So root mean squared. So you square it first, you take the mean, the average, and then you take the square root. And you will get I, which is the maximum amplitude, over square root of 2. Similarly, for voltage, you get this value. So the values that you get when you measure alternating current and alternating voltages using any instrument, electrical instruments, such as a multi-tester, are actually RMS values. So in the Philippines, our voltage lines is 220 volts, and that 220 volts is actually DRMS, a root mean squared voltage value. So let's now have an example. Okay, So, okay, we relate this in our local situation. So in the Philippines, the RMS voltage supplied by our electrical outlet is 220 volts. So this alternating voltage is varying at a rate of 60 hertz. So what is the maximum or peak voltage output of the outlet? Okay, so from the formula, Vrms is just equal to V, the peak voltage, over square root of 2. So therefore, I can solve for the peak voltage as square root of 2 times Vrms. So you just multiply 220 volts by square root of 2. And you will get 311 volts. So this is the peak voltage. So please don't be confused by the V and the V. I'm sorry, we don't have any other units. So this V here is a unit of voltage called volt. This is a quantity, physical quantity called voltage. So please don't be confused by this. So if mathematicians are actually watching this or looking at this equation, they will deem it mathematically wrong. But this is a quantity, this is a unit. Okay, we have so many inconsistencies in physics. So what does this mean? So this means that the voltage in the Philippines actually swings from positive 311 volts to negative 311 volts. So it swings from positive 311 volts to negative 311 volts. And the rate that it's swinging or changing or alternating is 60 hertz, meaning 60 per second, 60 times per second. So it will switch directions from positive to negative 60 times in 1 second. So that's actually very, very fast. So 60 hertz. So that is, this is the peak voltage in the Philippines. It's 311 volts. So the voltage will swing from 311 to negative 311 volts. Okay. So for another example, let's now try to calculate the current supplied to a laptop charger, alternating current supplied to a laptop charger. So we have here a sticker at the back of a laptop charger with a brand Dell. Sorry, I'm not promoting any brand. So the sticker on the back of the laptop charger says that it draws 10.1 amperes. So this is here. You can see it here that the input is 10.1 amperes from an alternating current source. So now if you connect this charger to our outlet, which is rated at 220 volts Vrms and frequency is 60 hertz, what are the average current, the square of the RMS current, and the current amplitude? Okay, let's first solve for the first problem. What is the average current? So take note, again, that the current is sinusoidal. So at one point, it's maximum, then it becomes 0, and then it becomes minimum, maximum, maximum. Now, what is the average value of this? So if you look at this graph, half of the time it's positive, half of the time it's negative. Therefore, the average is 0. So actually, the average of any sinusoidal function, sine and cosine, is actually 0. So the answer for letter A is 0. The average current for letter A is 0. Okay. For the second problem, what is the square of the RMS current? So the given current here, 10.1 amperes. So any given values here that you see, voltage and current, those are RMS values, root mean squared values. So for letter B, we are asked to find IRMS squared. So since that is 10.1 already, square that and you will get 102 amperes squared. So why do we bother solving IRMS squared or I squared? Take note that the power loss in a resistive device or resistive element depends on I squared times R. So knowing I squared, we can have an idea of how much power is it consuming. Of course, given the resistance, we can solve for the actual power. Okay. Lastly, we are asked to find the current amplitude. So similar with the previous example, we can find the current amplitude by multiplying the IRMS by square root of 2. So IRMS is 10.1. You multiply that by square root of 2 and you will get 14.3 amperes. So meaning the current input to this charger actually swings from negative 14.3 amperes, positive 14.3 amperes to negative 14.3 amperes. So like that. So it's swinging from positive 14.3 to negative 14.3 amperes at a rate, of course, of 60 hertz. So it swings at 60 times, 60 throw and crest in 1 second. Okay. So that's the end of the lesson, for the first lesson of this chapter. So for the second lesson, we will be talking about what happens when you now connect circuit elements such as a resistor, inductor, or capacitor to an alternating AC or AC circuit. So I will see you again in the next lesson.